Hey everybody, how's it going? Um, Pleasure to have you all here. So, this talk is called Shader Profiling and Optimization, work done by myself and one of our support engineers, Juan Uran, who's out of Colombia, who was not able to be here today. I'm Asa, and I work at Unity as a field engineer, where I help mid and large size Unity devs understand more about what they can do and how they should do things within Unity, as well as take their feedback and bring it into our dev pipeline. So, who in this room is a technical artist? Good. All right. Who is a graphics programmer? Some of you that might be the same thing in some cases, right? Who is a 3D modeler, artist, or texturer? Okay, cool, awesome. So everyone, all of us, all of you guys that just raised your hand, work with shaders on a daily basis, whether directly or indirectly. And even if you're not writing a shader or working on it at that moment, it is constantly doing work while you're in the Unity editor, drawing what's on your screen, and of course, actually drawing what's on the screen in your games and apps as well. So what are we going to talk about? We're going to talk about what a shader is and how do they work, which might be a little remedial for some folks in this room, but it's a good idea to just establish some base knowledge about shaders for folks who maybe aren't as up to speed on them. And also, if you are an artist, this maybe will give you some insight if you want to debug your own shaders or materials. Say you're coming from something like Shader Forge, where you have a little less understanding of what's going on under the hood. We're going to talk about where shaders fit into the main game loop, which kind of ties into that first topic, and then what tools are available to help and debug. That's kind of probably why a lot of you are here. And this talk is a little shorter than I wanted it to be, so we're going to go through them, but pretty quickly, and hopefully take away some key tidbits and nuggets. And then the last part is some nuggets of knowledge, just general shader best practices, stuff that we've documented at Unity, and I'll share that with you guys, and then also give you guys some links to some external materials that you can check out. What do we have here? This is the Atom demo, which was obviously a really remarkable demonstration of what's possible with 3D graphics, real-time 3D graphics specifically. Unity or not, it's impressive. But what is going on here? How is this getting drawn to our screen, and what role does shaders play? We can all reason about how you might move transforms or an object around a 3D space or write some gameplay logic. But at some point, all of the logic we're doing, all of the transforming of meshes and models and changing materials, all of that is basically shipped off to a magic box, and it then appears on our screen. So what's going on there? Let's just talk a little bit about that. So this is a very basic illustration of your graphics rendering pipeline. And so where is that magical place things are shipped away to? That's our GPU, our graphics processing unit, which, as most of you know, is a separate processor, oftentimes with its own dedicated memory. And that processor runs its own programs against every mesh that you pass into it. And so this happens sort of implicitly in Unity when you have a game object in the scene with a render of any sort, whether it's a mesh render, UI render. All of those are sending meshes to the GPU, along with maybe some textures and some other data. So what then happens? The GPU runs a program which its ultimate job is to create a giant list of RGB values that are also called your frame buffer. That is what gets drawn to your screen. So that means every single pixel is touched by a shader at some point, by a shader program. And so when I say program, a program is essentially made up of two shaders, a vertex shader and a fragment shader, or sometimes called a pixel shader as well. So when we talk about a shader, a program or a GPU program, it's literally almost always just a vertex shader and a fragment shader, but there's also some other tessellation and compute shaders, but we're not going to talk about those today. And so again, that means shaders are responsible for drawing every pixel on your screen. So if you put that in perspective, on a 1080p screen, that's 2.8 million pixels. That's a million on an iPhone 6 or 7. So there's a lot of lot of work going on your GPU, and understanding what that is and how we can optimize it is obviously important. And so just to sort of take a look at what we have on screen here, you can sort of see everything that leads up to the shaders running, right? The shader program is running there, right, in sort of the middle. But initially, we send our assets, our meshes, vertices, textures, all that stuff off to the GPU. And then every frame, we are preparing to render, so we're maybe moving some stuff around, changing textures, modifying materials, doing whatever we have to do on a frame-by-frame basis to make our app or game go. And then that's when the shader runs after that, after we have all of our inputs. And so I'm actually going to show you guys really quickly what these two shader programs look like, what a vertex shader and a pixel shader looks like. If I can figure out how to multitask. What is going on here? All right. So in Unity, this is sort of our demo project that we're going to be looking at throughout the talk. And in Unity, if you just create a simple shader, if you go down to the Create menu, Shader, and just do a standard unlit shader, what you get is a super basic but effective shader program. This can be a little dense to look at. It's obviously structured a little differently than some of the code you might see, but essentially what we have is up here, and I can try and zoom in on this a little bit for you guys. Nope. All right. What we see up here is, so we're basically establishing the name of our shader, setting up some properties. So here we have one called main text. So this is obviously going to be our texture that we can then drag and drop when we're in the editor. And then the most important thing that we're setting up here and what we're going to talk about today are these two lines here. So here we are defining our vertex program, our vertex shader, and our fragment shader. They're just called vert and frag, and we can see them mirrored down here, vert and frag. And this is our actual code that our shader, that our GPU is running. Yes? Yeah, I was trying to. Well, we're not going to be looking at this too much, but I'll try and figure it out when I get back into it. Oh, here we go. Is that better? OK, cool. So anyway, this is a super simple program, and we actually have that is the shader that is running on this object in our test scene that we're going to look at in a little bit here. So jumping back. One thing that's key to talk about, we talked about the frame buffer, this giant list of colors. That's something that typically is sent straight to your screen, but that's also what you can store when you're basically storing a render texture, maybe keeping it around for later use. It's kind of the same concept. It's that last phase when you have done all of your work in your shaders and have drawn something to the screen, you then can store it in a render texture, for example. And what's also key to note is that the first step right there, like as it's mentioned, does not run every frame, and you don't want that to run every frame because, again, these being two discrete units, your CPU and your CPU's memory, and then your GPU and its own memory, that communication process can be slow. And so we'll actually pin your mesh data on the GPU memory and then only update those based on transforms that you're passing in your prepare to render phase. And so this is also why you don't want to use functions like graphics.drawMesh. Don't want to really rely on those because they are sending that mesh data to the GPU every time. You put a few of those in your game, and especially on a lower power device, it's going to crush your frame rate pretty quickly. And so diving a little more deeply, what is a vertex shader and what is a fragment shader? So we saw some code there. What are they actually doing? So a vertex shader is a program, is code that runs on every vertex of every mesh that is visible in your camera frustum. So you have 20 models on the screen. Each of them have 100 vertices. All of those are going to have some sort of program running against them. And what is that program doing? So it's translating the geometry from a 3D space into the flat, essentially, screen space that you are actually viewing things through on your screen through your camera. And you can see this, again, if we were to go back to the shader, we could see some of the simple math that's happening, transforming by world. And you guys are probably mostly familiar with that. And then the pixel shader sort of picks up where the vertex shader left off and then leaves off and fills in all of the missing bits. So you have maybe a triangle that you're drawing on the screen. Sure, you have your 3 vertices. You've sort of established where those are going to be in the world, but then you have your pixel shader come in and fill in those bits. And we can talk a little bit about how that works too, and that's a process called rasterization interpolation. So rasterization, you guys hear about rasterized graphics all the time. What does that actually mean? A raster data is essentially, it's a list of it's a grid of rows and columns that contains data, and in our case, those are colors. Those are the pixels that make up our screen or our view space. And the interpolation phase is literally just interpolating between our 3 points. So right here we have a vertex that has a blue attribute attached to it, or blue color attached to it, and a red color attached to it. During the interpolation process, we rasterize, we put everything into a grid, which I'll show you right here. That corresponds to our pixels on the screen. And then interpolation is literally just linearly interpolating between these 2 points. So right here, we're maybe 50% green and 50% blue. And that's happening automatically. That process you don't have to deal with. That happens in between the vertex shader and the pixel shader. So why do we care about optimizing shaders? As we talked about, in general, shaders are running every frame on every mesh in your game. Vertex shaders operate on every single vertex in your mesh. So there's obviously balance there. The more complex your mesh is, the more times your vertex program is going to run. And the more complex that vertex program is, the more of a performance hit you're going to take. And then pixel fragment shaders operate on every single pixel within the triangles composed by these vertices. So again, if you're starting to do a lot of crazy math and work inside of a pixel shader, just realize that's going to run potentially millions upon millions of times. Because as we said, a 1080p screen has 2.8 million pixels. That's if you only write to each pixel once. If you are drawing complex scenes with tons of objects on top of each other, you could be doing 5 to 10x that or more. And then post-processes as well, because post-processes are actually, in most cases, just pixel shaders that are running on the entire frame of your screen. So then you are re-rendering, running a program on every single pixel again. And so, in general, on a per-frame basis, that means there's typically far more work done by your shader code than your own game code. Of course, GPUs are highly optimized to work on this data in parallel, and of course, optimized for the exact types of operations that we need, which are math and matrix math and transformations. So there's sometimes a debate about when to do calculations in a vertex shader versus a fragment shader. And optimizing vertex shaders in a lot of cases is kind of difficult if you're doing a typical use case and you're not trying to animate vertices, because in most cases they are simply taking that 3D geometry and manipulating it into view space. But there are cases where maybe you're doing some animation in your vertex shaders, and there are more optimized ways to sometimes run some of those mathematics that make a little more sense to your GPU, are a little more parallelizable, and we can talk a little bit about that. And implementation, so lighting and surface effects in vertex shaders are going to be much faster. So if I was to drop a light in my scene and it's hitting it's hitting our mesh, right? What it's actually hitting is a few vertices. And we send that to our shader, and our shader says, OK, cool, but we need to really go down to pixel level. We need to go to our pixel shader to know where this is hitting, where on our model this is hitting, and if we have a normal map, where specifically on the normal map this is hitting. However, you can do a simplified version of this if you just do lighting in the vertex shader. The problem then is that all of your lighting is then going through that interpolation and rasterization process, and it's just a simple linear easing. So you're going to have very harsh lines, and it's generally not going to look very good. It's definitely a low-spec optimization that, in general, is not really necessary these days, and it should not be done. But there are cases where you can still optimize your vertex shader. But in general, if you're concerned about image quality, a pixel shader is typically the better choice for doing work on a actual model or individual model on your screen. So let's take a look at what tools we have available to us. So Unity has a built-in tool called the frame debugger that you guys have probably seen and is super handy for basically seeing what's going on under the hood a little bit, understanding what is happening in my graphics pipeline. So if you just go to Window here, and then go down to the frame debugger, enable it, and it immediately grabs frame data for what's currently on your screen. You can also attach this to external players, which is super handy. And we can see here, sort of start to get an idea of what's going on. And we can also see that our actual game view in the background updates to show us what is actually being drawn on screen with each of these commands that is being sent to the GPU. So we're clearing, as we can see here, we see our full render phase, and then that's further broken out into different phases of drawing. So here, you can see, ultimately, we end up with the meat of what is drawing this to the screen, which is these draw mesh spheres under render forward, render loop job. And then we can actually inspect each of these draw commands and see the geometry that is being drawn, but also the shader properties here, which we can see actually the name of the shader right here, and then all of the various properties that are attached. So this can be useful for just trying to understand, maybe why something is drawing before or after something else, and understanding why something looks a little weird. You can, again, inspect your textures over here. And so for your example, maybe you're wondering, why do I see everything being drawn twice? And you can deduce right here that, okay, well, it looks like we're doing some shadow mapping, and these don't show on here, but on device you actually can see your actual shadow maps, and we'll see those in a second when we go to the native side. But if we were, for example, say, okay, you know what, this is not something we want to be doing. We don't even need shadows or want shadows. If I was to just go into here, select all of my spheres in the scene, and basically turn off shadows, we can now go back into the debugger and see that reflected here. So we no longer are now drawing these, running the shadowing shader process on these meshes, and it's a little more optimized. Maybe not a huge deal. This is not a very complicated scene, but in general, this gives you some insight into what's going on. However, this is not always adequate, right? Because we talked about here we have our shader, we have all these inputs going in, but we still can't really see what's going on under the hood. We don't really know what is happening. So, sorry, I should have done this before. There are a ton of tools out there to help debug shaders on the device level. And in general, this is something that you're going to find with each platform. You're going to have a specific set of tools designed to debug your shaders and what's going on in your GPU for that platform. So we're running OS X here, and Xcode has a great built-in frame profiler, which we're going to highlight here in a second. So I have already pre-built this project here. So we're going to go ahead and hit play. And you guys aren't going to be able to see it run, unfortunately, because it's running on an iPhone. But as you'll see in a second, that's not really super critical or important. So you guys may be familiar, if you guys are mobile developers, you may be familiar with this tab here, which gives you some general performance information as your app's running. If you haven't debugged shaders before, there is an amazing little option that's going to appear in 1 second as the app opens up. Right down here. So here we are capturing a GPU frame, and you can see our little scene is running here with our spheres rotating, and we can capture this frame. And so what this actually is doing is taking a grab of all of everything all the memory that our GPU is managing. So on a PC, this might be all of the memory on your NVIDIA GTX or whatever. On our phone, it's the portion of memory allocated to the GPU at that given time. So what do we have here? This is actually, we actually are rendering with Metal here. So this is using Metal rendering on iOS. So it'll look a little different if you use OpenGL, yes. But we have a little bit more difficult to parse view of what we were seeing inside of the Unity editor inside of our frame profiler. So, and we can actually see, because we're in development mode, we can actually see some of the functions from Unity that are happening here. So each of these represents operations that are happening on our GPU. And what we really want to look for is the meat of our drawing code, which is camera.render, right? So that is, as we know, the main camera rendering function. And from there, we can actually now drill down and see what is being drawn on our screen. So here, again, we have another nested hierarchy view of everything that is being drawn. So right now, we are focused on the upper left sphere. That's what we're drawing. Or actually, sorry, this is everything. So now if we dig down further, we go into drawing. We'll go into render opaque geometry. We have one transparent object, so that's actually going to be rendered later. Dig in here, and we now are getting down to the drawing of each of our primitives. And so what's super cool about this is you can look at, similarly to what we saw in the Unity frame profiler, all of the parameters. We can see our actual shader names to understand what shaders are being applied. So if something isn't performing as expected, it's super useful. And this, again, is a really, really much more detailed view of what we saw before. And sometimes it isn't super necessary, and that's actually not what we're going to focus on in this case, because as of right now, until scriptable render loops come along, you can't modify a whole lot of what's going on in here other than what you are seeing in the Unity frame profiler. But one thing that is super handy, so if you click on the FPS tab right here, we can actually now see, and I know that's a little tough to see, but we can see the contribution of all of our shaders to our total frame rendering time. And so we can see here, these are our 5 opaque spheres, and we can actually click in there to see them in the same view we saw before. But what's really handy is we can actually now look into our shader code. And so I will note that we're using Metal right now, so the shaders that you're seeing up here are in the Metal shading language. They correspond, they map pretty directly to what you see when we were looking at our simple shader before. But in general, there is going to be a little deduction that you have to do to try and understand what maps on in this shader to the shader that we saw in in Mono before. So we can see here we have, and this is actually breaking out for us what percentage of the shader time is devoted to a particular operation. So this is probably one of the better ways. Now these timings that you see, and then you can actually see the timing that they ran over here, so you can see in nanoseconds or microseconds what each of these is actually, the time that's taking to run on the GPU. But this is again, not going to always be super accurate, but as far as relative speeds go, this is going to help you understand what is actually slowing down your shader and where things are getting caught up. So this, again, is one tool. There are many tools to do this job. And so we could, you can spend hours looking through all of the options here and really trying to dig down into every shader. So we have our skybox here, things that you maybe don't even think about when you are building a scene, that everything has a shader attached to it. And maybe there's a way to optimize if you're at a point where you really need those precious milliseconds. So with that, so final thoughts on profiling tools. Different tools offer different features, and you're going to expect to have to try a few. for example, RenderDoc is a profiling tool that's really great. It's kind of wired into Unity. If you install it, you can launch it directly from Unity. But certain things maybe don't work the same as you'd expect. You're not going to get as accurate timing on your shader functions. So you're going to be looking at it more to see what's going on in the rendering pipeline versus using it to actually gauge timing and how long your shader functions are running. In a lot of cases, or in pretty much every case, each hardware manufacturer, as I mentioned before, has their own profiling programs. So NVIDIA has PerfHUD, and AMD has like Mali Studio if you're doing OpenGL ES on Mali, and they have their sort of Catalyst, their desktop trim. So in some cases, if you're not getting the data you want, you might want to actually try downloading the tool that corresponds to your actual GPU, because you may get more data and more useful data. Don't just give up, because unfortunately, you're going to have to use probably a few of these tools if you're getting down to the point where you really need them. It's kind of a pain, but there are tools out there. You just have to sort of give each one a shot and see what works with your hardware combination. So with that said, I just wanted to share some general nuggets with you guys that are kind of general best practices, and some of these maybe are more specific to mobile. I do recommend that you take a screenshot. If you're going to take a screenshot of anything in the presentation, these are probably good things to take a screenshot of. So I can only go over these really quickly because we're running low on time. But essentially, the first one is kind of a little confusing. What is a dynamic uniform? A dynamic uniform is if you need to do some math in the shader, ensure that it is going to be constant for that frame, so that it is not dependent on, let's say, a vertex attribute. So right here, we are setting a variable x equal to 4 divided by 33. You may say, oh, hey, this is a bad idea. I don't want to be doing math in my shader. I can just calculate it as a constant. But in some cases, maybe it makes your code a little more readable, a little more user-friendly. That will actually dynamically at compilation time get written as a dynamic uniform and will not be running every time you're running your shader program. So that's sort of a little optimization and usability tip. Multiply scalar values before vector values. This just cuts down on the amount of matrix math you're doing. Avoid discard instructions wherever possible, including alpha test. This is a big deal on mobile. It's why when you have a sprite-heavy game on mobile, especially older mobile devices, now it's a little less challenging. In the iPhone 4 days, it was pretty miserable. And just be careful with overdraw in general, because when you are drawing, especially with alpha and overdraw combined, that essentially means you have to constantly draw every single pixel. Your pixel shader is going to be, your GPU is actually going to be able to discard pixels that are behind or obscured at the pixel shader level. When you have alpha and overdraw and you're drawing a bunch of leaves on top of each other, because they have alpha, they will be drawn every single time because they don't know, am I going to be visible? They don't know yet, because it's a constant calculation and summation of the colors in that pixel, right? If possible, keep your calculations in a vertex shader. If you're if you're doing something like a time-based function to maybe transpose a texture coordinates to maybe do some sort of texture animation, do that in the vertex shader. You don't have to do it in the pixel shader. You can save a ton of time. You're only basically doing that calculation, let's say 4 times for a quad versus however many hundreds or thousands of times would be necessary if that was in the pixel shader for every pixel. Specify a right mask. That means essentially when you are setting values in your shaders, don't assign to fields that are not necessary. So if you have a position field, don't assign, and you're setting it to 1, don't set X, Y, Z, and W to 1. And you just want to set X and Y to 1, just set X and Y to 1. That will actually get optimized at compilation time, and your program will run just a little bit faster. Avoid branching. You guys have probably heard this one. Don't branch, especially on dynamic values that are going to change from one shader operation to the other, or from one vertex to the other. You can have some branching in your code. It's OK, but it is especially dangerous if you are branching on values that are changing every frame, because that basically ruins branch prediction on the GPU. And we are just about out of time, so I will speed through these other ones. This last one is actually really big. Avoid the impact of operations on your render model, or check the impact of operations in your render model. And on your specific hardware. So this is especially key on mobiles that use a tile-based rendering system that I have a link that you guys should definitely check out. Or in some cases, the discard operation is super slow on a lot of mobile devices. This is something that you will either find out painfully when you ship your app or as you're building your app, or you can try and get ahead of by looking into the GPU documentation and looking into the API documentation, whether it's OpenGL or DirectX, to understand which values maybe or which operations are going to be slower on that platform. And then I would just take a screen grab of these because we are running very low on time. But I'm trying to see if there's anything especially important. Use material property block instead of material set float or set color. This is a very, very important tip if you guys are doing a lot of animation in your actual material properties inside your shaders. Material property blocks are a far more optimized way than using set float or set color, which actually create copies of your materials every time you are doing that. So if you're doing this in an update frame, you're copying, creating garbage, and copying materials, creating garbage every frame, and are just generally going to hurt your performance. Use GPU instancing. This is a new, obviously relatively new feature. It's not on all platforms yet, but it's coming to more, as we heard Joe talk about in the keynote the other day. So keep your eye open for that and use it where you can. Here's the one last frame you can take away. The Unity frame debugger is obviously what we used inside Unity. Here are some of the more popular. Intel GPA is a great tool on the Windows side. I highly recommend it. And it works with typically any hardware to some extent. Obviously works great with Intel integrated cards, but in general, it just works. And then check out open source frame debuggers. These are actually, a lot of these are just as feature rich as some of the stuff we talked about that's mentioned up there, and you can actually customize it for your needs. If you are doing, if you're at that level, that is an option. And then, like as I mentioned before, definitely check out tile rendering on mobile. This is something that is not always straightforward and not something that people are super aware of the sort of limitations that you can run into when you're using it. But definitely worth checking out. And then on Unity docs, this optimization document is super useful. A lot of the stuff that we talked about a second ago came from there. And again, there's a lot of materials out there. And it's just it's definitely a task of sifting through them all, giving them all a shot, and you will end up with 60 FPS at some point after just a little elbow grease. So thank you guys so much for your time. I appreciate it, and I'll be around if you guys have questions after the talk.